Good morning. First of all, I want to thank Valentina Yalev for inviting me to give this talk that I am very pleased to do. My presentation is entitled Soft Computing for Transparent Synthesis of Geo Big Data. I will first introduce the notion of Geo Big Data, their sources and challenges. Then I will briefly outline the characteristics of soft computing that makes it appealing for designing explainable artificial intelligence solutions for Geo Big Data management. And finally, I will illustrate some case studies, the detail of which can be found in the cited papers. What is Geo Big Data? It is big data with a georeference on Earth. That means having either an explicit or an implicit geofootprint, that is a location and an extension on the Earth's surface. It is well known that 80% of the 2.5 trillion bytes of data created every day are georeferenced, so it is very important to be able to manage such data. Let us recall the definition of big data. According to the McKinsey Global Institute report, big data refers to data sets whose size is beyond the ability of typical database software tools to capture, store, manage, and analyze. And according to Wikipedia, it is an all-encompassing term for any collection of data sets so large and complex that it becomes difficult to process using on-hand data management tools or traditional data processing applications. So Geo Big Data inherits the 4 B's characteristics of big data. That is, high volumes, high velocity, great variety, and heterogeneous veracity. High volumes are relative and vary by factors such as time and the type of data. In fact, two data sets of the same size may require different data management technologies based on their type, for example, remote sensing data with respect to social data. These considerations therefore make it impractical to define a specific threshold for big data volumes. High velocity refers to the rate at which data are generated and the speed at which it should be analyzed. Data creation is driving a growing need for real-time analytics. In relation to high velocity, SAS Institute introduced the term variability that refers to the variation in the data flow rates. In fact, big data, especially Geo Big Data, velocity is not consistent and has periodic peaks, such as in the case of remote sensing data, which are acquired periodically depending on the revisiting times of the satellites on the same area. Variety refers to the structural heterogeneity in a data set as a consequence of the myriad of sources. They differ in gender, representation, projections, coordinate systems, structure and formats, transformations, and so on. This imposes a critical challenge, the need to connect, to match, and to cleanse the data received from different sources. And finally, we have heterogeneous veracity that represents the unreliability inherent in some sources of data and the imprecision and uncertainties of the data themselves. For example, georeference can be inaccurate or uncertain. Thus, there is a need to deal with imprecise and uncertain data, and this is a facet of Geo Big Data, which is addressed using tools and analytics developed for management and mining of uncertain geodata. One further aspect of Geo Big Data is their complexity. The georeference can be explicitly represented in the space or implicitly encoded by toponyms in linguistic form within textual data. There are in fact two main paradigms to represent Geo Big Data, which are known as the spatial versus the spatial. The spatial perspective is studied based on geometric reference systems that include coordinates, distances, topology, and directions, while the alternative spatial perspective is usually defined by textual place names, linguistic descriptions, and the semantic relationship between places. What are the potentials of Geo Big Data? Until recently, geodata were created by expert geographers and cartographers and GIS technicians. Nowadays, with smartphones and GPS, anybody can create geodata. We are in fact in the era known as neogeography, where amateurs can map anything by using digital mapping application and virtual globes, which tend to be free, and this has created what is known as the GeoWeb. First, we should distinguish between two large areas that involve Geo Big Data, the scientific area and the social area. The first area includes data obtained through scientific experiment or observations, typically coming with some control over the way data are generated, and with meaningful metadata that specify characteristics and semantics of the collected data. The second area mainly includes data product of human interactions, such as mobility traces, economic transactions, healthcare records, interactions on social media, often characterized by a lack of control over data generation and poor availability of the semantics. Let us see more in details some examples of scientific sources. Remote and in situ sensing data are collected across the electromagnetic spectrum, allowing optical, thermal, microwaves, and radio imagery and measurements. The first Landsat satellite was launched in the 70s, and since then we have a huge archive of data, of remote sensing data. As far as the European Commission Copernicus program, with the in situ and remote sensors, such as those on board of the Sentinel constellation of satellites, more than 12 terabytes of Geo Big Data are created every day. Another source of Geo Big Data that we can consider as scientific or better authoritative data are public administrations and environmental agencies that publish geodata on their web portals. These geodata comprise risk and hazard map, forecast maps, thematic maps, maps of commercial and territorial services. On the other side, the most prolific source of Geo Big Data are IoT and mobile phones that were more than 5 billions in 2010. Smartphones are equipped with many sensors nowadays and constitute the largest sensor network. Then we have volunteer geographic information, which is created within citizen science initiative by means of smart applications installed on smartphone. Let's think at the OpenStreetMap project, which reached 6 million users in 2016. OpenStreetMap's data are used freely by many applications for their high quality in urban areas. In fact, it has been estimated that in some cases they are more accurate and updated than official topographic maps. Finally, we have geolocated social messages created within social networks such as Twitter and Instagram and so on. Analyzing geotagging messages can be valuable for event detection and monitoring. Let's think at the recent issue related with the diffusion of the pandemic. Given all the sources of Geo Big Data, a new challenge of the research is performing their fusion in order to enable better decisions. The fusion can exploit the first law of geography expressed stating that anything is related to anything else, but near things are more related than far things. Then the geometric component plays a key role in the fusion. So, messages in social networks can be correlated with remote sensing data and sensor data, even human sensor data created by SmartApp, to get better ideas of where, when, and how environmental phenomena have affected the territory and impacted the society living there and the people's life. For example, the Harvard Institute has recently fused Baidu search engine query logs with remote sensing data of the parking sites closer to the Wuhan hospital, and they have observed an increase of traffic and an increase of queries about respiratory diseases, hinting to the outbreak of the diffusion of the pandemic in late 19. In order to allow better decisions, we need to turn Geo Big Data into value. That means into valuable information to extract useful knowledge. In fact, Geo Big Data are often characterized by relatively low value density. That means that data received in the original form usually has a low value relative to its volume. So to turn data into value, solution must be defined for implementing the so-called Geo Big Data value chain. This implies first defining data ingestion and extraction approaches for selecting, filtering, and generating metadata. Second, data integration within a geodatabase or spatial data infrastructure must be performed by manipulation, standardization, and normalization of the data and conflict management. Third, with the help of a domain expert who knows the problem, geoanalytics and geoexploration must be performed by querying, mining, machine learning to extract implicit information. Finally, geovisualization and interpretation of information by an expert is important to release to decision makers information whose process of production can be transparent and human explainable. Solutions have to be defined by considering a balance between the desired efficiency and effectiveness depending on the user requirements. Efficiency has to do with the ability to process high volumes at high speed at low costs, while effectiveness has to do with the relevance and appropriateness of the results produced by a process for a given purpose. In fact, there is not so useless as doing efficiently what should not be done at all. So effectiveness is the ability to extract useful information to take decisions by selecting reliable information, considering its veracity, and analyzing geobig data by considering its great variety. Solutions have been defined facing high volumes, high velocity, and great variety mainly. In fact, high volumes are dealt with cloud-based horizontal scaling architectures in which several medium-sized servers are flexibly connected as needed to store chunks of geodata. High velocity is achieved by distributed processing paradigms based on distributed processing infrastructure and, for example, Geo Hadoop, MapReduce, and GeoSpark, which allow geometric object representation and manipulation and querying with metric and topological operations. The great variety of formats and structures of geodata are integrated within NoSQL databases, and the standard web services of the Open Geospatial Consortium allow for the interoperable sharing on the web of geodata. But what about the management of the heterogeneous veracity? Not much has been done on this side. In fact, geobig data are often assumed as synonymous of fact, while this is not true. There is an urgent need of suitable approaches to assess and assure the quality of geobig data and to manage their conflict when synthesizing them. What are then the challenges for managing the veracity of geobig data? Semantic interoperability, first of all, is intended as the ability to integrate geodata based on the spatial and the spatial representation. For example, mapping geographic footprint of textual documents based on the place names within their content in order to enable spatial querying. Then we have quality assurance and assessment by representing imprecision and uncertainty of data and sources and modeling their fitness for use. In fact, quality is a relative concept depending on its intended usage. Finally, flexible and transparent synthesis of geobig data is needed. That means coping with distinct needs such as the redundancy, the conflicts, the complementarity of the data, and also assuring human explainability of the criteria used to generate the synthesis so that experts and decision makers can be aware of the semantic of the used data. Soft computing offers several opportunities to manage veracity of geobig data, since it is a branch of artificial intelligence that comprises methodologies that aim to exploit the tolerance for imprecision and uncertainty to achieve tractability and robustness at low solution costs. The main constituents are fuzzy logic, neurocomputing, and approximate reasoning, comprising both probabilistic and possibilistic reasoning. As far as semantic interoperability, the notion of fuzzy sets allows to represent the semantics of linguistic concepts, such as, for example, high, low, big. It has concepts with sharp boundaries having inherent graduality. Quality assurance and assessment can exploit fuzzy ontologies in which both fuzzy concepts and fuzzy relationships are represented to model ill-defined domain knowledge, and approximate reasoning can be applied to compute fitness for use of the geodata. As far as flexible and transparent synthesis, fuzzy aggregation operators allow to model decision attitudes and different importance, reliability, trust of the data. Fuzzy clustering also allows to generate groups with faint boundaries, thus are appropriate tools to model flexible and transparent fusion of Geo Big Data. First of all, I will briefly introduce some basic notions used in the following case studies. The notion of fuzzy set generalizes the notion of classic set so that the membership degree of an object is a value in the unit real interval. The membership function of a fuzzy set defines the semantics, for example, of linguistic concepts, of linguistic values of variables, for example, in this case, of the size of the petals of a flower. It allows to compute for each value of a basic domain of a variable, which is the real domain in this case, its degree of membership to the fuzzy set, so that some elements may partially belong to it. For example, in the slide you can see that the linguistic value small, medium and large of the variable size defined on the basic domain of the real values are expressed in centimeters are three fuzzy sets whose membership functions intersect one another so that one given value in the domain, for example 3 centimeters, can belong to both small and medium to distinct degree. The slide shows also a simple example of a fuzzy ontology, modeling a qualitative ill-defined definition of three groups of roses in the walled garden, the modern roses and the wild roses, based on the perceived aspects of their properties, which are the fragrance, the number of petals, the color, and the size of the petals. These properties can assume linguistic values whose semantics is defined by fuzzy set, as you can see for the values small, medium, large of the size. Based on this fuzzy ontology, approximate reasoning can be performed to compute the degree of belonging to the three groups of roses of a given instance, for example, observed and tagged based on the values, on the linguistic values of its properties. Finally, fuzzy aggregation operators can be grouped into three families to aggregate a number of arguments with values in the unit real domain to yield a unique value in the unit real domain as a result of the aggregation. Basically, they can be grouped into T-norms, which are not compensative and the result is below the minimum of the argument, T-conorms that are completely compensative and the result is above the maximum of the argument, and mean-like that are partially compensative and the result is in between min and max. The ordered weighted averaging operators, OWA operators, are a kind of mean-like aggregation operators whose semantics can be expressed by linguistic quantifiers. For example, the end, which is the minimum, is expressed by all. In fact, all arguments must be not null to yield a not null result. The or, which is the maximum, corresponds to at least one. In fact, it is sufficient that one argument is not null to have a not null result. And we can define a continuum of intermediate quantifiers between and or, such as a few, most, at least, and so on. The semantic of the OWA operators can be interpreted in terms of degrees of optimism and democracy of a decision attitude they apply. In fact, they can be mapped into a bidimensional space of two measures, as you can see in the table. The degree of honest on the axis that indicates the closeness to the behavior of the OR, and the degree of dispersion on the x-axis that indicates how many arguments are considered to determine the result. The honors indicates the degree of optimism, pessimism of the attitude of the aggregation. The dispersion, the degree of democratic, monarchical attitude of the aggregation. For example, the OR, in the case of values which have a negative flavor, implements a monarchical and optimistic attitude, while the AND a monarchical and pessimistic attitude, while the average is a democratic balanced attitude. The first case study I'm going to illustrate is on quality assurance of volunteer geographic information by constraining its creation through selecting perceived aspects of properties from a fuzzy ontology. The idea was to represent imprecision and epistemic uncertainty that degrades the quality of volunteer geographic information and in situ geoforensic observations. In fact, within a project founded by Lombardy region named Space for Agri, we had agronomers who went on field survey via Smart App to tag the phenological growth stages of observed crops. They had problems, however, in identifying a growth stage as described in the agronomic ontology, which was a classic ontology, in which they could see the shape of the different growth stages. In fact, they had problem in distinguishing these different aspects of the stages as depicted in the images of the ontologies, and also they have difficulties in observing the crop from far point of view due to the variability also of the crop growth stages in the same field. Also, the landmark automatically detected by the GPS receiver of the smartphones was inaccurate because it was outside the field on the road, so the tagged field was uncertain too. We defined a fuzzy ontology describing the phenological stages in terms of perceived aspects of the crops. This way, the determination of the phenological stage was performed by applying approximate reasoning that can associate an observed instance to the instant degrees to possibly several crop stages. We did the same for the landmark. We could exploit the sensors of the smartphone, the gyroscopes, to determine the directions of the camera view when shooting a picture, and we could associate the observation to distinct degrees to several fields in the direction of the camera, so representing the uncertainty of the landmark. As far as the flexible and transparent synthesis of Geo Big Data, and specifically of remote sensing and in situ data, the motivations for defining a soft approach are the following. Single approaches were used, but they were too crisp to generalize when changing study area and observation conditions, although they were transparent and human explainable. More recently, machine learning approaches have been applied successfully in several contexts, for example, for object detection and image classification. They are basically data-driven, but need large set of ground truth data for training, often unavailable in remote areas such as rural areas. Moreover, they are opaque and do not exploit available knowledge. Soft computing can combine the positive aspects of both the approaches above. It in fact allows representing ill-defined expert knowledge, and it allows combining knowledge and data-driven approaches with the need of a small ground truth data by explaining the learned criteria. Thus, it is compliant with what is known as explainable artificial intelligence. This is why we proposed a soft approach for the flexible synthesis of Geo Big Data, which is based on the way in which GIS technicians map environmental phenomena of interest from several geodata layers. And we have generalized this process, which is a two-step process. In the first step, thematic data layers, which are named contributing factors, selected from cartography and remote sensing data and products are selected and uploaded into the GIS. Then selection conditions are defined to segment partial evidence maps, which are binary maps of the phenomenon, identifying areas potentially impacted by it. In step 2, the aggregation of these partial evidence maps is performed by specifying Boolean aggregation operators that apply either the intersection, in the case of the N, or the union, in the case of the OR, of the areas to generate an environmental status indicator map of the phenomenon, which is again a binary map. The process has been generalized in this way. In the first step, soft constraints defined by fuzzy set replace the Boolean selection conditions so as to admit degrees of satisfaction in a unit real domain, determining partial evidence map with spatial units having a value in the unit real domain. In the step 2, OR operators replace the Boolean and OR operators. They are either specified by a linguistic quantifier by a decision maker or learned from ground truth data and are used to aggregate the partial evidence maps to compute a final environmental status indicator map with values in the unit real domain. The approach is efficient since it is a two-step process applied on each spatial unit that can be either an object in an image or pixel, one independently from the others. Thus, it can be implemented by exploiting distributed processing by partitioning the Geo Big Data into independent chunks, on which partial evidence maps are computed by mappers in parallel, and then performing the aggregation by reducers on each chunk, again one independently from the others. A different OR aggregation can be applied, which can be either specified by a decision maker to model the desired decision attitude, either pessimistic or optimistic, either monarchical or democratic, on each chunk, or it can be learned from available ground truth data in situ information so as to adapt the mapping to the local context. The approach, the first use case that I'm going to illustrate, implemented based on this flexible synthesis, was done within the European project GeoLand for mapping an indicator of anomaly on the vegetation cover in Africa at global scale. Several time series of meteorological data like temperatures and rainfalls, land cover and phenological data were first analyzed to determine partial evidence of anomaly for each month in a period of 10 years. This was done by defining soft constraints, determining partial evidence of anomaly as the complement of the normal distribution computed based on the long-term average of the meteo data and of the phenological data, so that the distance from normality determined anomaly. Then the partial evidence maps were aggregated by an OR determined by experts with a linguistic quantifier to produce monthly maps of anomaly. We tried several aggregation operators such as at least one to all. It was evaluated the correlation of anomaly maps with the El Niño event, and a high correlation was computed for the area of Horn of Africa that you can see with values of red indicated high anomaly. The second case study implemented based on the flexible synthesis was done within a regional funded project named Simulation ADS to map standing water from both remote sensing optical images and in situ observations by volunteers. Sentinel-2 optical sources were downloaded, data were downloaded for study areas with different kinds of standing water. For example, flooded areas or flooded rice fields or inland water. The spectral index were computed and segmented by specifying soft constraints which falsify the segmentation threshold defined in the literature on each spectral index to determine partial evidence maps which were finally aggregated by OWA operators learned from in situ geotechnical observation created by means of a smart app by volunteers. We could determine maps of standing water for the areas, and also we could explain the learned aggregation operators. As you can see in this slide, on the right panel, we could observe the different semantics of the learned OWA operators in each area, which are depicted with rectangles of different colors, since they have different hardness and dispersion, revealing that in some cases a concurrent aggregation of partial evidence is needed, while in other areas with different observation conditions and ecosystems, and complementarity of partial evidence was exploited. For example, in this case, you can see that they are more democratic. The aggregation operator learned for the Emilia area, which was characterized by flooded areas, with respect to the rice paddy field and Po area, which were characterized by human flooded areas, rice paddy field, or river in normal conditions. The third case study was again on this flexible transparent synthesis, was done for mapping landslide susceptibility. Several distinct models based on the weight of evidence produced distinct maps of susceptibility of the same area on the Alps. And we had to choose which one was the best. So we applied the flexible synthesis as an ensemble approach to fuse the results of these models. The synthesis was determined by modeling the decision maker's attitude towards risk. An optimistic attitude that wants to highlight only the most critical situation was obtained by specifying the most quantifier. That requires that most models were in agreement in order to map an area as susceptible to landslide. And instead, a pessimistic attitude was also applied that did not want to disregard anything for a greater security of people and infrastructures. This was defined by the quantifier at least 25% in order to map a susceptible area to landslide if at least 25% of the models were in agreement to consider it as susceptible to landslides. The last case study of this flexible synthesis was aimed at detecting periodic or episodic events as reported in social network messages, specifically in Twitter. First step was the selection, the collection and filtering of many single messages from Twitter dealing with an event of interest, such as, for example, traffic jam or sport game or music festival and so on. These messages were selected by specifying keywords relative to traffic jam, for example, in different languages or with different synonyms. So we collected a certain number of messages that were geolocated dealing with traffic jam. Then, in the second step, we aggregated such messages by applying a spatio-temporal clustering algorithm to determine the area and possible periods of time where the events occurred. The map, which is shown on the right, depict the areas with the pins of different colors, the traffic jams which were found in Bangkok city in the 6 months in the period in which we have collected the Twitter messages. We can also see that these traffic jams happen periodically, daily, in different hours of the day. To conclude, managing Geo Big Data calls for flexible and transparent synthesis capable to model their veracity of the data and decision makers' needs. Soft computing offers a suitable framework to define solutions which are both knowledge and data-driven and above all transparent, which means based on criteria that can be explained linguistically, thus realizing explainable artificial intelligence. This is a win-win solution that could be defined because it allows several levels of flexibility. It allows encoding ill-defined knowledge and ill-defined decision needs. It allows adapting to local conditions by exploiting small ground truth data. It provides human interpretability of the criteria and of the results. So, I thank everybody for the attention, and if you have any questions, I will be pleased to answer you.